Peek in Pig's pocket.
That's right, exactly. You just never know what's going to happen. Okay, it's on. Here we go.
It's here?
Yes.
Okay. Let me make a slideshow out of it.
Yeah, we should be able to.
Okay.
Should we have to know how to get rid of all that stuff at the bottom? Or will it just,
It's not connected.
because it's not in yours?
Oh, may I? May I see?
Yes, great. Okay. Can I do just a brief introduction?
Yes, please.
So I know some of you have had the pleasure of meeting Shears, but not everyone. But I love the story of how Shears discovered us. So she lives just around the corner in the apartments over there. And one, I think a Saturday, she had gotten word of a wonderful award that she had gotten as a young scientist in her home country of India. And she was so grateful that she wanted to go to a temple to give thanks. And so she looked up on the internet, and we are the nearest temple to that apartment building over there. So she shows up. She had not been in a Christian service before, and stayed for community hour, and we met for coffee, and we've been friends ever since. And
Yes.
so, so thank you so much for sharing your expertise with us.
Yes, thank you so much. Thank you, everybody. Thank you, Lori, for inviting me for this opportunity. So I'm going to talk about, and please let me remind me how much time I have. I can
An hour total,
Okay,
but you wouldn't
yeah.
have to fill all of it if you didn't want to.
Yeah, I mean, I can finish early if you want. So now I'm going to talk about our sun, especially when our sun is stormy, like they're erupting, and what happened with their eruption. Especially we call it like solar eruptions, and what would be the impact of those solar eruptions to the weather and their impact on Earth especially. So sun impact on all the solar planets, but here we are mostly talking about like what happens on Earth if there is a solar eruption. So before going into solar eruptions, just a brief, I'm pretty sure that you all are aware like what sun is and what are the specifications, but just to complete the story, I would like give you a brief out of it. So sun is our living support, and like from our childhood, I know that we are in existence on Earth just because of sun, the energy that what we got from what we are getting from the sun. So sun is our parent star, and it is the nearest astronomical observatory what we can work on. So there are a lot of other stars, galaxies that is really, really far away from us. But if we can understand sun, we can understand many billions and billions of stars which is already in the universe. So the age of sun. So sun is already 4.6 billion years old. It's a young age, so it's like in between their life, and it will go as per prediction, it will go another 5 billions of year. Sun contains 99% of the solar system mass, so you can imagine Earth is really tiny object in front of sun. If you combine all those 9 planets, their moons, all the asteroid, meteorites, everything together, it just comes in 0.004 or 0.014 or something of mass. So it's really, really huge. So when it comes to their structure, so sun is a gaseous body. It's not a solid body like Earth. It's just gas of helium and hydrogen mostly. There are some other gases like carbon, nitrogen, others, but mostly hydrogen and helium. It's in plasma form. So plasma means the gases with like nucleus, proton, neutrons in the nucleus, and the electron revolving on it. But if it's any atom is in plasma forms, it means their nucleus and their electrons is like separated. So plasma means like charge of gases. So sun is made of all plasma, mostly of hydrogen and helium atoms. So at the very core of the sun, these two gases of atoms have nuclear fusion, and because of that we got a lot of energy. And that energy convect from center, from the core to the outer layers, and as they convect, they changes their property, and that's how we change their names from one to other layer. So just after the core, there is a radiative zone where the energy radiates from one to other location. And the next zone is called convection zone. Convection zone is very similar as you see boiling water in a pot on gas stove. So what happens if you put a boiling pot with water on a stove? It's like as the pot got heat from the bottom, all the water atoms go up and then have a bubble, and then bubble got flowed and then come back. And this rotation comes like for several times. So in this convection zone, the yellowish part, it's all the energy, all the atoms and plasma molecules, they just come down and up like this, like convection, and that's why this zone called convection zone. After that, the most familiar layer that we know about the sun, so we can also see with the naked eyes, which is called photosphere. So when you see sun, you actually seeing a outer layer, which is called photosphere. It seems yellowish when you see it like in the morning or in the evening, or whitish, because it contains all the wavelengths. So that's how the combination looks whitish. The temperature, as we go away, or as we coming out from the core to the outer layer of photosphere, it's decreasing as normal physics, that as we go away from the source, the temperature should get down. After photosphere, there is a layer called chromosphere, which is a little reddish in color because of the other atoms like nitrogen and carbon, and because of that, this very thin layer after photosphere, which we call chromosphere. Chromo means color, and that's how it's named. You can see it with your naked eyes, but only during the corona. So last corona, or I could say not corona, solar eclipse. So last time solar eclipse happened in May 2024. If you were able to see that, it was visible from the northern America. So if you saw it, so during the solar eclipse, there was all black, and there was some reddish lines out in the outer surface, and that's the time then when we can see corona with naked eyes. After that, the most dynamic layer comes, called corona. It's still dynamic because we don't know much about it so far, and it's also contained the most everlasting solar physics unanswered question. I'll discuss about that later. So because of this outer layer, the convection zone and the photosphere and chromosphere and corona, there are a lot of instability happen in the surface, and because of that, there are some eruptions happen. So just to make it easy, like how that become, or not in this slide, a lot of for this slide. So I'll go forward for the next slides, and I'll tell you like how those eruptions happened. So before going into detail, I would like to just tell you like what are the unanswered questions so far. I don't know why it seems like this in this, but it's okay in my computer. So just couple of questions I would just discuss, that why all we are working on it from last many decades and still working on it, why we are putting our hours and hours every day. So there are some science questions, which is the first one is coronal heating problem. I guess you heard somewhere here and there. It's just not the solar physics problem. It's actually the problem for all the astronomy, because all stars works very similar. So what happened with the corona, the outermost layer, if you remember, after photosphere. This colored zone, this dynamic structure here, that is called corona. And what happened? So one more time with this image. So as I said that all the nuclear fusion happened in the core, and energy is just coming out, and that's how the entire sun made of. But for example, just imagine there is a candle or any light source. It could be bulb or any fire, something. Let's suppose there is a candle, and if you are very close to the candle, you feel more heat. As you go away, the heat is less. It's very simple physics. And it is happening on sun also. So when you are at core, temperature is very high, like millions of billions of Kelvin. As you go away, radiative zone, temperature is little less. Convection zone, there is less temperature than radiative zone. Photosphere is very less temperature. It's like 6,000 Kelvin something. But as you move away from photosphere, like in corona, temperature gets really high. It's like around 15,000 Kelvin. So you imagine from 6,000 Kelvin to 15,000 Kelvin, or also this 15,000 Kelvin is average temperature. The temperature is also get high, other than like more than 15,000 Kelvin. And scientists, we don't know why this temperature is increased very sudden after photosphere. Normal physics law, what we already know, it failed, so we are working on it. And last publication, what I have, we tried to answer this problem, but we only solved 16% of the entire problem. So we're still working on it. We don't know the answer. Second question is solar wind origin. So as I said, like there is energy is coming out from sun. So the plasma, which is originated from core, but still it's not finished at the outer layer. So it's just not finished at this boundary layer. It's still emitting. So solar wind, it's a solar influenced plasma which is moving outward from the sun and covering entire solar system. So that is called solar wind, and we don't know what exactly the source of those solar wind, because I mean, we know that they're coming from the core, the energy is coming from the core, but solar wind has their own behavior. Sometimes it's accelerated, sometimes it's decelerated, temperature is sometimes very high, sometimes it's low. So we don't know exactly what is the reason behind all the behavior of solar wind. So this is another outstanding problem. We are working on it. My last year paper was on that problem, second problem, but again, we are not fully resolved that question. We are still working on it. We just gave one, and I mentioned also that here, we found one structure within the solar wind called magnetic switchbacks. As its name says, switchbacks means something is like switching back. Yeah, like that. So we got some magnetic structures we call switchbacks. Their behavior is something like that. They're coming and going forward. And so in our paper, we discussed that these magnetic structures, as they go away from the sun, they stretched out, and simply the magnetic energy turned into the kinetic energy. It's just a simple example that we gave. We tried to resolve this issue, but still, we couldn't resolve the 100% of it. The other problem that the scientists in solar physics are working on is solar cycle. So sun is, as I said, like sun is very dynamic, and its behavior is also dynamic. So right now in this period, you saw auroras. Have you seen auroras? The northern lights from here, from Iowa City. And as you are living in this city from long time, you were not experienced this 5 years ago, right? There was no auroras 5 years ago. There was no aurora 10 years ago. But if you lived here a long time, there was some auroral activity would be, I'm sure, 12 years ago or somewhere, if you remember. And again, it was stopped for 10 years, and then it would be before that. So why is that so? Because sun have a cycle of 11 years. So right now, where we are living right now from 2024 to 2026, it's called a maxima period, where sun is very active and erupting a lot of energies. So during that time, we have a huge amount of energy that hit Earth, and because of that hit, we got auroras kind of features at the lower latitude as well. But auroras is always visible to the poles, but to the lower latitude like Iowa City or Washington or Texas, it's very rare events. So this time, yeah.
I don't want to interrupt, but that seems like the strangest of all the things that you have there, because an 11-year cycle that it goes through again and again.
Yeah, we don't know why.
Any speculation at all about why?
Okay, so why the answer would be like, what explanation we can give? We don't know. The exact answer, we don't know. So that's why it's an outstanding problem. But the approximate, the physics, what we know, based on that, what would be the reason is, as I said, like sun is a gaseous body. There is no solid stones like Earth. So the rotation is also a dynamic. As Earth, as we rotate like fully. From north to south pole, we rotate at once. But in sun, it's not happening. So in sun, the pole and these poles have a different rotation period, and the equator, the center part, has different rotation period. So it's changed from pole to the equator. And because of this rotation, these magnetic field lines are become so twisted, and because of that, the possibility that the rotation completes after 11 years, and that's how we are getting this maxima period and the solar minima period. But still, it's theory. We don't have proof of it. So let's see what will happen in the next few years. So if you have any questions, this is just basic of sun, and after this slide, we'll go more into the one kind of eruption. Okay, and you can disturb me anytime, like you interrupt me anytime. So one question for all of you, and I know you all know this, just for being engaged. So you heard those words, climate and weather, and if you can tell me which is weather, A or B.
Say again.
So you heard that word, climate and weather. So there are two pictures here, and I want to know what is weather. Weather is.
What is weather?
Mm-hmm.
Weather is what?
A or B.
Oh, A.
Okay. Everybody is agree on A? Okay, perfect. So it's simple. Climate is like if there are a long-term change, we call it climate. We call it like a warming, what do you call? Global warming. So global warming is part of climate change, but weather is like winter to fall, fall to summer. So it's changing very frequently. That's why we call it weather. So why this question? Because next term what we are going to use is space weather. So space weather is a variable condition in space driven by solar activity that influence performance and reliability of spaceborne and ground-based technological system. And why we are worried about this? Because in this era where we are living, we are very much dependent on the technology which is on the space-based or the ground-based. I personally can't imagine my day without phone, or I mean, all of you, I guess. So I cannot go anywhere without GPS or the satellites, the entertainment that you're getting. It is all because of the technology what we have in space and connected through the ground-based instruments. So we have to be worried about this weather as we go out and check whether it would be sunny today or not, and that's how we plan our day. So we have to plan our space weather also, that whether sending rockets is good, or depending on our GPS today, it's good or not, like that. So what are the main drivers? I'm just telling you names. I'm sure that it would be very new for you all, but just be with me. I'll tell you like what it is. Solar flares, high-speed solar wind streams, solar energetic particles, and coronal mass ejection. And in next couple of slides, it's all about the coronal mass ejection. So the simple thing in physics, unlike biology or medical field, is that the names are very understandable. So if it's something like flare, it means that something is flaring. It's mass, it means something is mass. Ejection is ejecting. So physics is very easy to understand. So all the names that you can simply understand, like high-speed solar wind streams, that it means what it names. So next slide. It's all about the story of coronal mass ejections. So I'll talk about how those build up in the solar surface, how they erupt, how they travel from the sun to Earth, and what happened when they arrive, and what would be the impact of it. So as it names, called coronal mass ejections. So means some mass is ejecting from the corona. The corona, the outer surface of sun. And in short form, we call it CME. So I'll use CME word in later slides. So let's start with the buildup. Okay, before going to the buildup, why we are worrying about CMEs. So CME is actually the most massive eruption from the sun. It's very dynamic. So at the background that you're seeing, it's actually the size of, so this is the size of sun, not 1:1, but you can imagine like how it would be, big would be. It's a simulation. And this is size of Earth. It should be more smaller, but just to imagine. This blue lines that you're seeing here, it's a magnetic field all around Earth. And this structure here, it's called magnetosphere because of magnetic fields around us. Solar wind, and this tiny dots that you're seeing moving towards Earth, these are actually solar wind. So it's like continuously moving outward from the sun and like spreading throughout the solar system. And this is surface, and this block that you saw just moving that side, it is actually a CME. And why it is important? Because it's really huge, massive, energetic plasma bulb. So it's all made of magnetic field and plasma. And why we are worrying? Because on Earth, the most outer layer of Earth is magnetic field. So if something is coming with the magnetic field, they can interact with magnetic field and disrupt our system. Another thing within the CMEs are plasma. So our ionosphere, just after this magnetic field, we have ionosphere, and if those plasma interact with our plasmasphere or ionosphere, it can also disrupt our system. So that's why we are really worrying out of it. Or I can give you one more example to worry about CMEs. So have you seen a movie called 2012? So in that movie, a scientist gave a reason that Earth got cracked, the tectonic plates got cracked, or we call it pralay, I don't know what is in English word, but so the humanity got like destroyed after that. And the main reason they gave is CME. If a really huge CME come and interact with our system today, now, we are over. All the humanity, all the Earth system, magnetic field, plasma sphere, atmosphere, water, everything will be like disappear in seconds. So fortunately, we don't have such huge CME so far. There is one really huge CME was erupted from sun last 3 years back, but it was not Earth directed. It was somewhere other direction, so we saved. So
there's really nothing that could be done about that.
So last 8 years, I'm working on this phenomena, and so far we are very close to predict those stuff. But if it's really coming, if it's a nominal CME, like if it's 3,000 kilometer of speed and mass and density, we can save our satellites. That we can do now after a decade of research. But if it's really huge, we can't move Earth from its orbit. So if it's there, then we can't do this. But so now our prediction and our space weather forecast system is that strong that we can predict 2 days before when CME is going to erupt. And that's how we can save our space-based instruments or ground-based instruments.
And what would you do with them? Because you wouldn't take them down.
Yes, so thank you for that question. We cannot take them down, we cannot deorbit them because it's 2 days of period is very less. But how we save them, we switch off them. So if we are switching them off, it means the energy or the particle and plasma and magnetic field, they cannot interact with those systems, with the instrument, and that's how we can save it. And we did it. We did it for our NASA's Wind spacecraft last year. We did it 12 years back. We did it for ACE instrument. If you heard in news last year, there was SpaceX satellite. It just got deorbited because of one CME. So we should take care of like when it's coming and when it's not.
This is the greatest danger, isn't it?
Yeah, all of them, like amongst all. So how we are observing them? So
This is my question.
yeah. So how to observe them? So thanks to last 1 decade of all engineers working with us, they built like amazing instruments. So let's start with, no, Earth is very messy. Let's start with sun. So the closest ever spacecraft we have is Parker Solar Probe, and the good thing with the Parker Solar Probe is like it's designed so well that it can survive within the corona itself. So I told you like coronal temperature is 15,000 Kelvin something. So this instrument, human-made instrument, can survive in that 15,000 Kelvin temperature. The question is, how is it possible? Any material on Earth cannot survive this temperature. So what happened with this is that it has mirror made of titanium and some other material that can reflect all the energy and temperature back to the surface, like mirroring the surface. And that's how wherever this spacecraft is close to the sun, they just reflect all the energy back, and sometimes we just close it when we are really close. So that's how we are surviving. So it's orbiting. So if you imagine this is sun, so Parker Solar Probe orbit is something like let's go very close to the sun and then let's go back with the big orbit, elliptical orbit. So this is one, and it has all cameras. It has in situ spacecraft instrument to observe magnetic field, plasma, etc. So with very close to the sun, and then we have solar orbiter, which is in between sun-earth line, so we can observe in between what is happening. We have stereo, which is on the same orbit where Earth is rotating. So we have like 2 spacecraft. We can see, so this is sun. We have like 2 spacecraft here and there, so that we can have like 3D view of sun all the time. At Alvan point, so there is a Lagrangian point between sun and Earth, which can, if you put any spacecraft on Alvan point, it will be there forever, and then it can see sun all the time. So we have most of our spacecraft on Alvan point. So we have Wind, we have SOHO, we have ACE, SDO. These all are on Alvan point, and we are observing sun 24 hours. And there are some other instruments that you're seeing here. It's all instruments are within the magnetosphere. If you remember the previous image, there is a magnetic field and there is a magnetosphere. So all these instruments are within the very close to the Earth, like within the Earth magnetosphere. And combining all those spacecraft, we have visible light instrument. So we can see sun, we can get a picture of it. The beauty of sun is it's emitting all the energies in all the electromagnetic wavelength. So if you heard about radios, yes, we can observe sun with radios. If you heard about UV lights, yes. Visible light, yes. Not electromagnetic, X-rays, gamma rays. So all those electromagnetic wave spectrum, we can observe sun in all of those instruments. So combining all those spacecraft what we have, we are observing sun in all possible ways. So in next slide, you can also see some of those instruments imaged directly. So this is one of the SDO images. And it's real image, it's not artifact. And what you're seeing here is called sunspot, or how that made of. So these lines, these are all magnetic fields. So in your school days, you did that experiment with the iron, iron is with the magnet, and you see like how all those magnetic field lines coming out. So this is very similar to that. So all the magnetic, so imagine that this black spot is a north pole, and somewhere a white is a south pole, and all the magnetic field lines are connecting to south to north like that. Yeah, and why that happened? It's also very interesting to understand. So imagine, I told you that sun is dynamic, rotation is very different from one to other place. Imagine these are all magnetic field lines. And if you imagine a rubber band, and once you have rubber band pulled into two sides, and then you twist it one after one, at one point that rubber, it's elastic is so stretched, and it will break, right? It will break. If you are having a rubber band in two poles and you switch it, twisting it one after one, then at one point it will break from somewhere. And that's what happened over the sun. And when this magnetic field line twisting and then break, this become a less temperature compared to the surface. And that's how when you are seeing it from the instrument outside, you see there's a less temperature blob here, and that's what we call it sunspot. And it's pictured like a black spot over the solar surface. So what happened? When this break, like breaking is okay. When this break, it's all a magnetic energy. So energy is stored in these rubber bands kind of structure, the magnetic field lines. And when it break, it erupt like a lot of energy outward from the sun surface. And that's what we call solar flare and CMEs. So solar flare and CMEs happen like together. So solar flare is basically observed in X-rays. That's why we call it solar flares, and it's very sudden eruption. And CME is like combined structure, like it's stored magnetic energy and coming out as a bulb, and that's how we call it CME. Okay. And also you can see like how huge this sunspot could be. And you can see sunspot with naked eyes as well if you have solar glasses. So if sun is very active, like nowadays, you can see those sunspots with naked eyes too. These all are real images that we got from the instruments. Yeah, so this is eruptions, how that eruptions happen. So size of Earth is this, and this huge sun, and this is one magnetic loop from North Pole to South Pole that you can see. Like there is a sunspot, and you can see those the magnetic structure out of from that.
So how big is that?
Yeah, that's what I'm saying. This is Earth, so this size compared to the Earth, it's really, really huge. Yeah, and imagine this loop is twisting and just coming out. And when it coming towards Earth side, it can interrupt our system. And that's the bottom image is showing like how they erupt. So this is how they erupt, because it's just not magnetic field. So magnetic field also trapped plasma in it. magnetic field and electric field, like, they work together. And all the plasma, all the electrons and protons, they trapped in those magnetic field lines. And when they erupt like all together. So that's how the eruption works. We call it flux rope, or this is instrument picture again. So this black spot you are seeing here is the size of sun. And this is called, there is one instrument called SOHO, and we have, what we do is, so sun is really bright, really bright. And if we just click picture of sun, we cannot see these eruptions because these eruptions brightness is really less compared to the real sun. So what we need to do is, we have to minimize the brightness of sun. So for that, what we do is, like, we made an artificial occultation, artificial solar eclipse all the time for 24/7. So this black spot you're seeing here, it's actually an artificial occultation within the instruments what we have in the space.
So you didn't have to move the moon.
No.
It's a lot more efficient.
Yeah, it's a lot of work. So we choose the easiest way to do it. So which are,
Something about driving interplanetary shocks, and what does that mean?
okay, so interplanetary shock is like this CME that you are seeing here. You can imagine a car is moving. So if car is like car or plane, whatever is moving object. So if it's really in high speed, then you can feel a shock before the moving object. And that's really happened with the CME as well. So when there is the bulb of plasma and magnetic field is moving, so that is like moving so fast that the background solar wind creates a shock in front of it, and that's how we call it interplanetary shock, because the shock appeared in the Sun-Earth line, like interplanetary system. That's why.
What are some of the strongest effects on the Earth that you've recorded?
Okay, so in 1959, it was blackout in Japan, and like all the power grids, all the electric system was disturbed, failed for 3 days. There was no power at all. So that was the biggest storm that we observed so far. There was one more. Last May 2024, the same event when we saw the auroras. That was also a very huge event, but thanks to our community, we predicted that event well before. It was not that similar as 1959 event, but it was huge enough that can disrupt, but we are safe.
So that means that with instruments, researchers like yourself just intensely study the surface of the sun.
Yeah.
And they can sort of see from the changes that are happening when something big
Yeah.
is likely to happen.
So you saw this last image, this one. So we are tracking this. So if these two sunspots are really complex, so there are chances like having more eruptions. And so we are tracking this. If there is really intense complexions in this, we predict them like well before. And that's how we are. And we predict like how strong a storm would be when it arrives Earth. And also we can, with tracking these surface, we can also predict like which direction of CME would be. So that's how we can predict like how much impactful it would be if it arrived Earth or not. Yeah, I already discussed this one. So what you're seeing here is just, so sun is there, Earth is, if I just compare this image, so Earth would be somewhere there. So this huge structure, it's actually very impactful if we are very close to sun. But as it moves away from sun a lot, when it arrived Earth, the intensity is getting like very less compared to what exactly it was at sun. So it is moving like that, and you can also see some structures here. So this is a bright structure. We call it magnetic cloud, like the outer surface. And if you see this one. So this structure is actually this one, and you are seeing in this image the outer surface here. Just before this, so for example, there is a solar wind at background. This structure is erupting. So what it will do is like it sweep out all the material, all the plasma, all the solar wind material. And after this, there would be a blank. So you see this blank, there is no solar wind particles in it. So this blank called core of CME. It is very dense, it is very less dense, very less temperature, very less magnetic field. So when this CME arrived on Earth, we can observe all those structures. We can observe shock, as you said. We can also observe this high intensity structure, and then we can also see less density or less temperature structure. And all of these 3-4 parts have their own behavior or their own impact. This is one simple example how it arrived on Earth. So I would wait for one more time of it. So it erupts, and it has magnetic field, I said, and Earth is also having magnetic field. So Earth is also like a magnet, have magnetic field lines both as equal as a circular, but because of continuous solar wind sweeping out, so our Earth's magnetic field look like a crab, like very, okay, so let's discuss this first. So CME is coming and it has magnetic field lines like this. Earth has magnetic field lines like that. And then when it interacts, so magnetic field lines interacted and it pushed it back to night side of the Earth. And again, as I said, like magnetic field lines trapped plasma. So when it interacts again, plasma, it comes back to the Earth, and that's how we got auroras all the time on the North Pole, North and South poles. But this is not always the case. When there is a very huge CME, those lines can be very compact, and the interaction would be very close to this, and that's how we got aurora effect or northern lights from the lower latitude as well.
That looks like an incredibly violent collision.
Yeah, it is. And it's also not all the time CME can interact with Earth magnetic field. As I said, like having an interaction between magnetic field lines, it's very important they should be opposite to the direction. Something like sun's magnetic field lines is like southward, and Earth magnetic field lines is always stable northward. So if this has happened, at very rare case, there is interaction with opposite magnetic field lines, then only we can get these kind of storms.
Good question.
Yes.
Okay, so obviously it affects our electrical systems, our internets, and all that, okay? What about its effects on organisms? Humans and animals and insects and so on?
Yes, the other community working on it. So we basically don't work on it, but there are psychological changes with it's proven. I am not going to talk about which is not proven, just hypothesis, but it's proven that hope you all know that moon has 27 days of their rotation, and that's how female body works. So female got their period just because that how moon is working. Similar to that, sun has impact on our psychological system. There's one paper came out in that they said like if sun is really active, like in the maxima period, the people's psychology and all the animals, all living beings have vibrant behavior. As sun goes calm down, like in the minima, people also got so calm down. It's proven with very certain number of people, but it's on like published research, so I can say that.
So much of what goes on in our organisms is electromagnetic.
Yeah.
And so are people who have problems with hearts, with rhythms in their hearts and so on, are they affected by the sun?
Not directly, but again, so as you're saying, like human body is also an electromagnetic system, and if you can also experience it. So as I said, like Earth's magnetic field is from the south to north, and if you sleep, actually you sleep by heading your head towards south side. So your body magnetic field will be aligned with the Earth magnetic field, and you really feel so calm if you get, like once you get up in the morning. It's proven. I'm not saying it's not proven. So Earth system works with our body. You feel like I tested, and I feel really anxious when I'm not sleeping in a good position. So that effect. And if you are really feeling uneasy and you just want to keep calm without doing anything, I would recommend to sleep with the south and north side, and then you feel good.
You mean you sleep with your head to
Southern side.
We're good, we sleep heads to the south. So either north or south, but to be on an axis.
Not the opposite direction. Opposite direction will change your entire system opposite. So your head should be in the south side.
Okay, good.
Yeah.
Good.
So
Let me just interject. I mean, you think like it sounds like, oh, this is weird. But think about seasonal affective disorder.
yeah.
And that is the sun, and it's, you know, that lower light has huge effects
Yeah.
on people. So it's not surprising.
Yeah, it's not at all. Another impact on living beings. So sun is also having cosmic rays. So during the maxima period, the cosmic rays from the other galactic object, astronomical object, it's less because sun is like blocking them. So that time also the cosmic rays can impact in so cosmic rays is like neutrinos coming to the earth, like ground, and neutrinos can really impact all the living organism, the water bodies what we have. So not directly, I don't have any paper to refer, but it has impact. So our system or all the living beings also impacted or also behave as solar cycle happens once after another one. Yeah. Any question? Okay. Okay. So the impact. Again, I'm not talking about the Earth surface because I don't work on Earth surface. I'm not from the Earth. Or I would say, so I could tell you this. So I started my research journey from the sun itself. So when I started my PhD, I was looking at what's happening on the sun surface itself, like from the sunspot, etc. And I moved to my first postdoc, and I started working on interplanetary system, like how CME works when it is in the sun-Earth line or in interplanetary medium. And then I did my second postdoc when there was very close to Earth side, like L1 point, what is happening. And now, right now, I'm working on a project or space mission which is already in the Earth magnetosphere. So as people say, like as you study, you become down to earth person. I'm actually becoming down to earth person. So I'm like slowly coming to Earth, Earth side. We'll see. So how CME impact on Earth system? So very first thing that we are worrying about is our satellite because we are really highly dependent. This generation is really dependent on Earth system satellites. So and these eruptions, either solar coronal mass ejections or solar flares, they can direct impact on it. So they can change our instrument. They can disrupt instruments for a while or maybe forever. They can also deorbit them. So if their speed is really high, they can also deorbit our spacecraft. If a spacecraft changed, and also the ground-based instruments, highly impact on GPS system. And right now we are really dependent on it. I guess, I mean, if you individually think about it, not really. Means you know the way to your home and you can come back here and there, that's okay. But if you are flying, so all those flying system, aircrafts, airlines, they are highly dependent on GPS system. If any one signal is missed, there would be like huge accidents. So this is really important. We should know this before, and we are trying from last 7 or 8 years, this prediction system, the forecast, space weather forecast. So we're still a little far, like not little, I should say, really far from the very good prediction, like 100% of predictions. We can predict those eruptions 2 days back. Like if it's something happening today, we can predict them 2 days before, but it's not enough because in 2 days we cannot do much changes. So if we know them before, at least before month or so, we cannot predict more than a month before because sun is dynamic, it's changing every time. So 1 month is like doable stuff. So we are trying to like we are working on it, and hopefully very soon, because in last 5 years we are evolving a lot, especially with the engineering stuff, and also like last 5 years the AI is helping a lot. So yeah.
So I'm curious, you are a person of faith and someone, I think, who sees the spirit at work throughout the universe. So what is most awe-inspiring to you about the work that you do, or what you see in your work?
Okay. So I can give you like very small example if it's not taking a lot of time. So I was fascinated with astronomy from my childhood. I was seeing stars and I thought like, oh, we are so tiny. We have a tiny soul, and all the problems what we have, see the stars, they are huge, many lives will be there and like that. So I was fascinated with that, and I decided like I'm going to be astronomer, not the astronaut, because I don't want to go to space. I just want to read it. I just want to learn that what it is. So astronomer, not astronaut. So I decided like when I was 7-year-old, that I want to go for astronomy. And then during my master, I actually worked with the top scientists in India. There was summer internship. I was working with them, and day and night for two months, I was working on active galactic nuclei, which is like black hole, but outer surface of black hole. Entire night we were observing, and day we were sleeping. The 2 months was hell. So one day after 2 months of our study, there was a gathering, and all the students came to us, and they said like, you're doing fascinating job and it's really look good, but how you feel that, and the galaxy what we were observing, it was 36 billion light years far. It means that what we are observing was not in the existence, it was like it was dead. So but we were getting their light now, so we were observing it. So one student came, undergrad student, and she said that you are doing good job, but what would be the benefit of human beings on this? Like there's no benefit. The object is gone. You are studying to just knowing more science, but there's no direct impact. And that night I couldn't sleep because I was thinking like 2 months I spent, and I was planning to take it further for my career, and I was thinking what would be the result of my 30 years or 40 years of research if I'm not able to contribute to the society, like humanity direct. And I also didn't want to change my astronomy field. So that's how I moved to solar physics, because sun has direct impact. Yes. So of course, not only the CMEs or not only the solar flares or eruptions that we are looking at. Sun itself, the energy what we are getting right now on the Earth's surface, it's just because, or we are in existence on Earth because of the energy what we are getting from sun. And that motivates me every time. So we are doing something which can help humanity to to grow or to plan their next year, not in hundreds of years, just next year. So that's motivates me every time. So.
So could you explain
Uh-huh.
the concept of solar wind? Because in space, in a vacuum, there wouldn't be wind.
Oh, okay. So there is no vacuum at all.
Okay.
Uh, so it's like, okay, so it's you can understand that I also learned that there was a vacuum in space when I was in a school, but as I grow, I said like, no, no, no. So you can understand this as like, as we were kid, we said atoms are the tiniest object we know, but as you go in a higher classes, you say like, no, 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 atoms is also made of electron, proton, and neutron. And then you go in a higher schools, and then you say like, no, no, electrons are, neutron is also tiny object. So space is not made of vacuum. There are particles, there are mass, there are temperature. Yeah, they're moving around. So yeah, just to be clear. It's moving outward from the sun. So all the sides, like on 3D, all the sides are moving away. We don't know. So sometime it got accelerated on Earth side, but sometimes it's decelerated. So we don't know the behavior exactly. We are working on it. We'll hope soon we'll get
Job
it.
security.
Yeah, actually, we actually don't want to solve everything. so, so right now, what I am doing. So, University of Iowa, it got the largest funds, the biggest funds from NASA for a mission called Tracers. So Tracers are actually a twin mission, to twin a spacecraft having similar instruments and moving from this to this direction, night side to the day side. So this is day side, this is night side, and these instruments, they are crossing the poles, North Pole and South Pole. These two spacecraft crossing like this. We call it cusp, where these all magnetic field lines like coming here. This is very first time we are observing cusp with two instruments and trying to know like all those solar wind CMEs, which when it comes here, the connection happened with the magnetic field lines, and what happened, like how much particle is precipitating to the Earth, and we are trying to quantify that energy, particles, everything with the tracers. And this is one of, so Space Science Department, Astronomy Department has 3 instruments on this spacecraft, and we all are getting our bread butter from it. So, yeah, so it is really amazing. Last year, July, it launched, giving us amazing data. We published 5 papers so far, all our new science, what we got. We're working on it, one more, not only one more, entire community. So we have more than 30 scientists, senior scientists from NASA, Berkeley, UCLA, SWIRI, and of course, Iowa. Yeah, and 30 senior scientists, more than 20 postdocs, undergrad students, graduate students. So we have a big team who's working on it and getting really, really nice results out of it.
I have a question.
Yeah, please.
I went with a group of people down to Missouri, and we watched the solar eclipse 6-7 years ago. And one of the things that the people talked about, and we observed, is that all of a sudden all the birds got silent.
All the burst?
All the birds.
Birds, oh, okay.
Very, very quiet.
Uh-huh.
And I don't know if it was because of something direct or indirect. It was just that,
Okay.
the light was changing.
Yeah, it's just because of the light changing. So animal works with the lights, their psychology works, that if it's sunset, they just go silent and go to sleep. And that happened during the solar eclipse. There's no other reason out of it.
Very striking.
Yeah.
All of a sudden.
We experienced that when there was a partial eclipse. We were in the north of Iowa, kind of above.
Mm-hmm.
And even with the partial eclipse, the birds stopped singing.
Yeah. And I
So I'm
wanna.
wondering, one last question, or?
Yeah, this is just last slide. This is me, and this is last 2024 Aurora that I was talking about. We had, sorry? And this is Iowa City. We were somewhere in highway, just stopped our car. So was really beautiful. And I had a paper on this event, and that is also came out of the news. So that's all. And
Oh,
yeah,
that's wonderful.
that's all.
Oh, thank you so much.
Thank you. Thank you so much.
That was fascinating.
It was great interaction.
I'm just impressed with how the sun and the earth get along. With that bad breath. How long will the tracer program continue?
So
Since it's in infancy.
So NASA gives money in chunks. So initial life of tracers was for 15 months, which is going to be over in February 2027. But we are requesting for extending mission. It will go for another 3 years, and we are very hopeful that we'll get it.
Has the data been beyond what you had hoped to find?
I'm sorry?
Is the data better than what you had hoped to have gotten?
Yeah, so every time we have to set a goal. So with this 15 months of period, we have goal and we are trying to get that, and we are very close to that. And once we get that close, we have to give them another science objective. And if NASA team is like convinced with that new science objective, we'll get the extension in our mission. And it will go like, it's very good engineering, so it will go for long life.
So you can see all the direct implications, all the money involved,
Yeah.
all those satellites and all the things that can be harmed by
Yeah.
solar weather. So, yeah.
Yeah, if anybody has any last question. Okay, I took a lot of time, isn't?
Thank you so much.
Thank you. It was great interaction. Okay.